Hey everyone, and welcome to This Explainer. Today, we are taking a seriously fascinating journey into the trenches of back-end engineering. We're going to tackle a massive, real-world challenge right from the ground up, scaling a location-based proximity service. Think about the apps you use every single day, like Yelp or Google Maps. You know, when you pull out your phone because you need to find the nearest coffee shop or maybe a gas station, there is a staggering amount of robust architecture working behind the scenes to get you those results pretty much instantly. So today, we are going to break down exactly how that works under the hood, and more importantly, how on earth you actually scale it. Okay, let's just do a quick run-through of our agenda so we know where we're headed. First, we'll look at the Proximity Database Challenge. Second, scaling the business table. Third, we'll get into structuring geospatial index data. Fourth, we'll diagnose the read-heavy bottleneck. And finally, number 5, we'll look at sharding versus read replicas. Let's dive right in.
So let's start with a really massive question. How do you scale a map for 100 million daily users? Just imagine that for a second. 100 million people, all opening their phones right around dinner time, all searching for a restaurant at the exact same time. When engineers are faced with that kind of scale, honestly, it's super tempting to just panic and start blindly throwing industry buzzwords at the problem. Oh, we need microservices, we need to shard everything immediately. But as we're going to see on this journey today, throwing complex buzzwords at a production system is absolutely not always the right answer. In fact, you'll see that sometimes the simplest architectural choice is actually the most elegant and scalable one.
All right, part 1, the Proximity Database Challenge. Before we can scale anything, we really have to understand the core entities we're working with, right? So, to make these massive location searches even possible, we have something called the GeoIndex table, and it works right alongside the business table. See, searching across a massive 2D map using just raw latitude and longitude is incredibly slow for a database. It's just not efficient. So, we use these brilliant engineering algorithms, things like geohashes or quad trees, to basically convert that giant 2D map into simple 1D strings of text. This geospatial index table is basically the magical bridge. It takes that 1D string, which represents a specific little grid on a map, and it maps it directly to the IDs of the businesses sitting inside that grid.
Moving right along to part 2, scaling the business table.
Okay, so our baseline is set. Now we hit our first real hurdle, which is handling the massive data set of the business table itself. To scale it, we just follow a really logical, straightforward process. First, we identify that our dataset, let's say it's 200 million businesses, is simply way too large to comfortably fit onto a single server's hard drive. So, we've got to split it up. The absolute easiest and most effective approach here is to shard the database by the business_ID. And why do we do that? Well, because this specific sharding scheme ensures that your data load is perfectly and evenly distributed across all your servers. You aren't just clumping all the busy New York restaurants onto one server that's definitely going to crash under peak traffic. It distributes the load beautifully and keeps your operational maintenance super easy.
Next up, part 3, structuring geospatial index data. Now, before we even attempt to scale the GeoIndex, we have to figure out how we actually structure this data under the hood. How do we map these geohashes to the business IDs? We've got 2 main options here, and option 2 is the clear winner for production. Let me explain why. If you go with option 1, you store one geohash, and then you basically just cram every single business ID for that area into a giant JSON array in a single row. The problem with that? Well, say a new coffee shop opens up. The database now has to fetch that entire array, scan the whole thing to make sure there aren't any duplicates, and then, here's the kicker, it has to lock that entire row to prevent anyone else from updating it at the exact same time. Honestly, it's an operational nightmare. Option 2, on the other hand, is brilliant. It simply creates a new row for every single business using a compound key. Adding or removing a business becomes a super simple, instant operation, and you have exactly 0 row locking.
All right, that brings us to part 4, the read-heavy bottleneck.
Okay, 1.71 gigabytes. This right here? This is a huge aha moment. When engineers hear 200 million businesses, the immediate assumption is, oh man, we're going to need massive clusters of hard drives just to hold this spatial index. But actually, if you build an optimized index like a quad tree, the entire mapping dataset compresses down to less than 2 gigabytes. 1.71 to be exact. That means the entire globe's geospatial index can easily, comfortably sit right in the working memory of pretty much any modern single database server. It proves that storage space is absolutely not our bottleneck here.
So, if storage isn't the problem, what is? Well, the reality is our constraint is entirely read-heavy. Just think about how you actually use a map app. You've got millions of users constantly opening the app, dragging the map around, zooming in and out. That generates massive volumes of read requests to find nearby places. But on the flip side, how often does a new restaurant actually open or change its name? Rarely, right? The write volume is incredibly low. Because we have this extreme read-to-write ratio, a single database server, even though it holds that entire 1.71 gigabyte index in memory perfectly fine, it just won't have the CPU power or the network bandwidth to process millions of incoming user searches all at once. Basically, the server's going to choke on the network traffic way before it ever runs out of storage space.
And this leads us perfectly into Part 5, sharding versus read replicas.
This is the ultimate architectural trade-off. We need to pick the absolute right tool to solve our read-heavy bottleneck. And here we see the stark, high-level philosophical difference between our two scaling options, distributing the data versus duplicating the data. With database sharding, we take our index, chop it up into smaller pieces, and put a different piece on each server. With read replicas, we take the entire, complete index, and we just make perfect, exact clones of it across multiple servers.
Now, database sharding introduces a pretty massive trap for this specific use case. Sharding is incredibly complicated because all that routing logic has to be added directly into your application layer. Your code suddenly has to act like a traffic cop, figuring out exactly which server holds which tiny piece of the map before it can even run a basic search query. It is significantly harder to develop, deploy, and operationally maintain. And remember what we learned just a minute ago? Our whole index is literally only 1.71 gigabytes. Chopping up a dataset that tiny across multiple servers is just total architectural overkill. Read replicas, on the other hand, absolutely crush it here. They are the ultimate winner. By creating exact clones of our database, we solve our exact bottleneck. Remember, we were running out of CPU and network bandwidth, not storage. So, by adding read replicas, we instantly multiply our CPU power and our network capacity. A load balancer can just take those millions of incoming read requests and seamlessly spread them across our entire army of replicated servers. It handles the massive read volume effortlessly, and the best part is, it keeps our overall system architecture incredibly simple to maintain.
So I want to leave you with this one final provocative thought to kind of chew on as you go out and design your own elegant backend architectures. If your data set easily fits in memory, is sharding ever really the answer? You know, we so often rush to the most complex, buzzword-heavy solutions because, let's be honest, they sound impressive. But as we've seen today, true architectural mastery is really about deeply understanding your data size, diagnosing your specific bottlenecks, and then simply choosing the easiest tool that perfectly solves the problem. Definitely keep that in mind the next time you're building out a system. Thanks so much for joining me on this explainer, and keep building great things.